You are probably familiar with this common emitter configuration of biasing a transistor. Using this configuration, you will be able to make an inverter, switch, amplifier, and many other useful circuits. How do you know what are the resistors' values exactly? In this configuration, the transistor is biased based on emitter current IE, and I am going to use this configuration to make a small signal voltage amplifier finding each resistor's required exact value. My goal is to amplify a very small signal to high enough to feed to a power amplifier. For example, making an audio MIC preamplifier. The input signal will be fed to the base terminal of the transistor, and the amplified signal will be collected from the collector terminal of the transistor. Just like this. How do we find out all components' values to bias this transistor Q1 at beta equals 100? Well, let's do the DC biasing first for this CE configuration, and finding out the components' values for DC biasing for this transistor at beta equals 100 and IC equals 1 milliampere. To do the DC biasing, we skip all AC sources and capacitor connections. After removing all AC sources and capacitor connections, the circuit will look like this. Now, I've denoted the voltage in collector is VC, voltage in base is VB, and voltage in emitter is VE. We need to set the collector in the middle of VCC and VE. How do we calculate resistors' exact values for a transistor DC biasing? Let we say VE equals 2 del VBE. After putting all values and doing the calculations, we've found VE equals 0.8 volts. Therefore, RE equals VE over IE. After putting the value of VE and IE in this equation, we've got the emitter resistance. RE equals 800 ohms. We've assumed that the collector current IC is approximately equal to the emitter current IE. I've used a closest standard resistor value for RE is 820 ohms. And using the standard resistor value, once again, we've found VE is equal to 0.82 volts. And we've decided the voltage at the collector terminal, VC equals VCC plus VE over 2. After putting the values of VCC and VE, we've got VC is equal to 4.91 volts. Now, we are focusing the voltage across RC from the circuit diagram. Using Ohm's law, IC/RC equals VCC minus VC. After putting the values of VCC, IC, and VC in this equation, we've got the value of collector resistor RC is equal to 4.09 kilo ohms. The closest standard value of RC is 3.9 kilo ohms. We know transistor beta is beta equals IC over IB. In this example, we assume the beta is equal to 100, and therefore putting all values in that equation, we've got the base current of this transistor is equal to 10 microampere. For nominal value of IR2, IR2 equals 10 IB, and we obtain IR2 is equal to 100 microampere. If IR2 equals 10 times of IB, then IR1 will be IR1 equals IB plus IR2. And after putting the values and calculations, we've got IR1 is equal to 110 microampere. From the circuit diagram, it is clear that VB equals VBE on plus VE. We know the transistor VBE on equals 0.7 volts, and from previous calculations, we've got VE equals 0.82 volts. And we finally have got VB is equal to 1.52 volts. Now, using Ohm's law, VB equals IR2 times R2. After rearranging and putting the values, we've got R2 equals 13.81 kilo ohms. The closest standard value is 13 kilo ohms. Again, using Ohm's law, IR1 times R1 equals VCC minus VB. After rearranging and putting the values, we've got R1 is equal to 68 kilo ohms. We've determined all the resistors values for the biasing of the transistor.
Now this is the time to go back to our original circuit diagram where all the AC sources and loads were connected.
To analyze the AC small signal, connect all DC source to 0, replace the transistor with its small signal model, replace all capacitors with short circuit. The circuit will look like this. The AC equivalent of the CE amplifier. Here, our SIG is the microphone internal resistance. Ri is the input resistance seen by the base terminal of the transistor. Rb is the Thevenin equivalent resistance of R1 and R2. Rpi is the responding resistance for VBE. Gm is the transconductance of the transistor. Ro is the collector output resistance. This capital Ro is the output resistance seen by the collector terminal. And Rl is the load resistance in our case, which is 33 kilo ohms. Just have a look at the block diagram of a voltage amplifier. Using simple voltage divider rule, Vi is equal to I over R sig plus I times V sig, and Vo is equal to RL over Ro plus RL times AOC times Vi. Here, AOC is the open circuit voltage gain. After rearranging these two equations, we can get the actual voltage gain Vo divided by V sig is equal to I over R sig plus I times AOC times RL over RO plus RL. If we can, find out the values of RI, AOC and RO. Then, we will be able to get the actual voltage gain of our amplifier circuit, because we've already got the other parameters values for the equation. And from this equation we can calculate the output voltage as well. Let's go find out. From this model we can get I is equal to RB parallel Rpi. And we know that Rpi is equal to beta over Gm. And Gm is equal to IC over Vt. From this model, we also get Ro is equal to Rc parallel Ro. And we know that the open circuit voltage gain AOC is equal to minus Gm times Rc parallel Ro, and there is not much difference if we ignore Ro, therefore, AOC is approximately minus Gm times Rc. After doing all the calculations, we've got I is equal to 2.53 kilo ohms. Rpi is equal to 3.3 kilo ohms and IC is equal to 79 milliampere and Gm is equal to 0.03038 ampere per volt. And we can get Ro is approximately Rc, where Rc is equal to 3.9 kilo ohms. Now, we can get the value of open circuit gain AOC is approximately minus 118.482. Finally, we've found, for 1 millivolt of input, the output voltage with the load of 33 kilo ohms, Vo is equal to minus 76 millivolts. We can say, for 10 millivolts to the input, we will be able to get minus 760 millivolts to the output. That's pretty good. Capacitor selections.
In this common emitter voltage amplifier, we are using 3 capacitors C1, C2, and C3. We just need to find out those values.
The equation to determine the capacitance is C is greater than 1 over twice pi Req, F sig. For C1, Req is the equivalent resistance seen by the capacitor. And Fsig is the minimum signal frequency. For the capacitor C1, the equivalent resistance Req1 is Req1 equals a sig plus I, which is 4.3 kilo ohms. And the C1 is equals to 1.8 microfarad. For the capacitor C2, the equivalent resistance Req2 is Req2 equals O plus L, which is 36.9 kilo ohms. And the C2 is equals to 215.6 nanofarad. For the capacitor C3, the equivalent resistance Req3 is Req3 equals 45.731 ohms. And the C3 is equals to 174 microfarad. Finally, we've finished our calculation for this common emitter amplifier circuit design. With all the components value, the circuit looks like this. Let's go to see what's going on the bench for the circuit.
I have set up this in auto mode, and first of all I'm going to check RC. Which is 3.8 kilo ohm in this multimeter, which is supposed to be 3.9 kilo ohm, but I have found here like 3.8 kilo ohm because the parameters has some tolerance. Next, RE I have chosen for 820 ohms, but I have found here like 833, 34, just like 30 ohms. And R1 I have chosen for 68 kilo ohm, but I have found here like 66.5 kilo ohm. And R2 I have chosen for 13 kilo ohm, but I have found here 12.85 kilo ohm. Okay, and this resistor I have chosen 33 kilo ohm. It is almost exactly 33.1 kilo ohm. And these two capacitor is if I wanna check the capacitor values. Okay, so once again the resistor here, these two resistors will make like 1 kilo ohm because my signal resistance is 50 kilo ohm from the 50 ohms from the function generator. So I have just connect here like 910 ohms. This one is 50 ohms and this one is 910 ohm, but I have found 906 ohm plus 52 ohms, altogether 959 ohms, and plus 50 ohms from here, that will make us like 1 kilo ohm. So now I have here this power supply, that means the battery is 9-volt battery. So let's check the battery's voltage first. 9.1619 volt. I need to check the capacitance, so I'm changing this to capacitor, but almost similar. And this capacitor is 206 microfarad. .3 microfarad. So I have seen all this value in this multimeter for those components here. So now this is the time to connect the power supply. So 9-volt power supply, just connected. So I'm going to check the voltages first. I'm going to check VE from here, 800.8 volt. I'm going to check VC, 5.29 volt. So VV is 1.400 volt at this. So the actual value VCE is 4.49 volt. So that means the transistor is in active forward region. So the input is connected here. This comes from the function generator. My function generator is here. I'm feeding from channel 2. So the channel 2 is set up sine wave 505 Hz and amplitude is 10 millivolt. And I have already connected channel 2 from the oscilloscope to see the input voltage, and then channel 2 is there. This is channel 2, the magenta color, and channel 1 is output for the amplifier, and this channel 1 is yellow color in there. So from the screen I'm going to measure the parameters. If I hit this button, this is gonna record 7 single shots. So like now I can see from the screen the channel 1 peak to peak voltage is 900 millivolt, which is the output from the amplifier, and channel 1 peak to peak voltage is 7.6 millivolt, which is the input for the amplifier. So if I calculate the gain of the amplifier, is the peak to peak voltage is output is 900 millivolt divided by 7.6 millivolt. So I have got here 118.42 millivolt. The gain is 118. So in the calculation we have seen like the gain was 76 millivolt. That is happens because of the parameters of our components is not accurately as described in the calculation in the theory. So there is little bit changes, tolerances for these components here. It's like little changes of the resistance, little changes of the microfarads, and then little changes of this like voltages. That's makes the changes for our calculation to the bench in the practical. So the gain is currently, I have got like 118, you can say. So just finding out the changes for 1 millivolt difference of the amplitude. If I change the amplitude from 10 to 11 millivolt, and nothing, I have changed only the amplitude, and then I'm going to see the differences. Just hit this button, yep, and then I'm going to see the difference. For channel 1, the peak to peak is like 1 volt, that means 1000 millivolt. It is showing that 1.04 volt. And for channel 2, the peak to peak is 6.6 millivolt. So now I'm going to see the differences. The previously there was like 900 and now 1040. So peak to peak differences. So the peak to peak differences is 1040 minus 900, so 140. So for 1 millivolt changes in the input, the output is changed like 140 millivolt. And the gain in this case 1040 divided by 8.6 from the screen, it is 8.6. The gain is just a little bit changed, which is 120. The gain is almost same, but we can see the changes for 1 millivolt in the input. The output is changed like 140 millivolt. So that's the beauty of the amplifier. So you can see the amplifier already amplified. It did its job, like amplified the signal from the input to the output. 1 millivolt changes in the input and it gives you 140 millivolt changes to the output. So this amplifier is basically designed for like small signal, which is not good for more than 20 millivolt, because if we just use this one for more than 20 millivolt input, and then we are going to lose the shape of the output signal. For example, so if I just increasing the value, and then we see output input. So if I increase more, and then you can see the shape is not staying as like the input one. You see the input and output, both shape is changed. So this is best. I have seen only less than 20 millivolt input, and then we can see the output shape is like exactly as like the input signal. So that's why it is called like pre-amplifier. So this signal is going to be fed to the power amplifier, and then we can get the actual voice to the loudspeaker or somewhere we need. If you like this video, please thumbs up. See you next time. Thanks for watching.